Hey guys. So in this video, what I'm going to show you is the wave nature of sound, how it travels through the air, and primarily the way that sound waves behave when they are inside of columns of air. So we had a lesson about this the other day, and I don't think it went that well. So I wanted just to completely redo the lesson. Um, and then this video will be up on the YouTube page, and you guys can take a look at it. So hopefully it will help you out with the assignment. Okay, here we go. So imagine you have a speaker, right? This thing produces sound. The way that it produces sound is in the form of a longitudinal wave that radiates in every direction around the speaker. So if you have your speaker, it goes in front of it, it goes above it, below it, to the sides of it, and behind it in every direction. It radiates outward like a sphere. So check this out. Over here, this is the direction that the wave travels, like that. And if you look at the circles, those represent like wave fronts. So I want you guys to think of a wave front as like literally the front of the wave. Those wave fronts are going out in every direction, and the wave travels out in every direction. So remember, when the wave and the speed of the wave and the propagation of the wave front are parallel to each other or in the same direction, that is what is known as a longitudinal wave. Now, all of the stuff that we learned the other day about waves, meaning with wave speed and wave frequency, and wavelength, are all applicable to sound. But one thing about sound makes it a little bit easier in that the speed of sound is a well-known constant in the air. So the speed of sound in air. Let's call this V. S. It's 343 meters per second. Now that's how we usually experience sound, through the air. But we could also experience sound through, say, water or through some sort of solid object like a wall, through any number of materials. So the speed of sound, of course, is going to depend on what material the sound is traveling through. So for example, through the air, speed tends to go rather slow relative to the other types of materials that we have. So through gases, through air, slower. As it travels through liquid, say like water, it will travel faster. And if it travels through a solid, it will travel faster still. Okay? But for today's lesson, we'll focus only on the speed of sound in air. Because what we're going to be talking about in just a little bit is basically what happens to the sound waves when they are traveling through some sort of air column, like a pipe. We see this a lot with musical instruments. So let's go ahead and jump right to it. Okay, so for this one, this is what we call a pipe or an air column with two open ends. All right, so I'm going to write here two open ends. In this particular example, what we see happening here is we have a node right in the middle of the pipe and antinodes happening at the ends. So here's the first thing that I want you guys to notice. When we're dealing with open ends, at the open ends, you will always see antinodes happening, okay? So here we're going to see an antinode, and over here, we will see an antinode as well. Always at open ends, you see antinodes. Okay, so when you see two antinodes and one node for a pipe with two open ends, this corresponds to the fundamental frequency inside of this pipe. So this is going to be our F1. Now, look inside the pipe. We see that we have, in your solid line, half of a wave, and in the dashed line, we have the other half of a wave. So we see Um, Actually, that's wrong. It's actually a quarter of the wave in solid and a quarter of the wave in a dashed line. So let me say that one more time. Our solid line represents a quarter of a wave, and our dashed line represents another quarter of the wave. So when we put these two together, we get half of a wave. Okay, so the full length of the pipe represents half of your wavelength, so that the wavelength is equal to twice the length of the pipe. Okay, now without getting too much into the math here, this is going to be our fundamental frequency, F1, and our fundamental wavelength, lambda 1, which is going to be equal to 2L. We learned about standing waves on strings the other day, and when you got a sound column or an air column with two open ends, the behavior is quite literally exactly the same as the wave on a string, which means that this is going to be right here, V over 2L. So let me say that one more time. We have behavior that is exactly like a standing wave on a string that has two closed ends. But here's the thing that you need to notice. For our two open ends in this situation, we have one node, two antinodes. Let's look at the next one over. Again, we have two open ends. We see two nodes and two antinodes. Now, when you got two open ends, you're always going to see only two antinodes. Only two. No more, no less. So what you got to be looking for is the number of nodes you got. Okay. So since this thing behaves the exact same way as a standing wave on a string, we can assign it the same formula. This is going to be F2. This is going to be F2 with the associated wavelength lambda 2. So if we remember from that lesson, our wavelength was L and our frequency was V over L. But to make this a little bit easier, let's say that this is twice the original frequency, and this is going to be half of the original wavelength. Let's see, wavelength 1 over 2. So it's going to follow the same pattern as before. Okay? Let's look at the next one now. Again, if you feel that I'm moving too fast, remember you could always pause, rewind, and rewatch. Okay. Again, we have two open ends, but now we see three nodes. So let's write that down. We got three nodes. Okay. So this is going to correspond to the third frequency, so our F3, which is going to be 3 times the original frequency, or we could say 3V over L, over 2L, excuse me. And then our wavelength 3, which is going to be 2L over 3, or we could simply say the original wavelength 1 divided by 3. So nothing new here. It's the same formulas as a standing wave on a string with two closed ends. So when you have two closed ends or two open ends, the behavior for the standing waves is going to be pretty much exactly the same, except On your closed ends, you will always see nodes, and on your open ends, you will always see antinodes. But like I keep saying, the math is the same. Okay, let's look at the next one now, which is what happens when you have one closed end and one open end. So this is where it gets a little bit different. So let me write over here on the top, one closed end, one I'm not sure what's going on here. Oh, I see. It's locked. Yeah. Okay. One closed end, one open end. So remember, on a closed end, you'll always see a node, and on an open end, you'll always see an antinode. So let's take a look at what happens in the first case. I'm going to call this F1, and I want you guys to notice that there is a node over here on the closed end and an antinode here on the open end, right there. Now the math for this one is slightly different than before, but we can still figure it out. Over here, what we see happening is only a quarter of the wave is present inside of this closed end when we have one node and one antinode. So let's go over here. We got our length L equals to quarter of the wave. Let's call that wavelength 1, which means that our wavelength 1 is now 4 times the length of the pipe, which is going to make the frequency 1 V divided by 4L. Okay, let's look at the next one over. Now the next possible situation is where you get 2 nodes. So over here we have, for F1, we have 1 node, and now we're going to see what happens when we get 2 nodes. Again, we must always have a node on the closed end and an antinode on the open end. Okay, so let's see what's going on with this one. Here's our antinode. Let's see what's going on with this one. So between those 2 nodes, we see a quarter of the wave, and then over there on the right, we see another quarter of a wave. Actually, no, between the 2 antinodes, we see half of a wave, and then we see a quarter. Okay, so in total, what we see is a half plus a quarter, which is equal to 3/4. So for this one, we see that the full length of the pipe is equal to 3/4 of the original wave. Or actually not the original of this one, which makes that this wavelength equal to 4L divided by 3. Now our original wavelength was equal to 4L. This one is equal to 4L divided by 3. So we could express this as the original wavelength divided by 3. Let's go ahead and call this wavelength 3. Our next frequency is going to be 3 V divided by 4L. Now, this part's super important. The next possible frequency is not F2, but rather it's F3. So it's equal to 3 times the original frequency F1. And then we can start to see a pattern for the next one, and then any subsequent ones after that. The next possible harmonic here is when you get three nodes and one antinode. Again, you're always going to see one antinode, but what changes here is the number of nodes that you have. So F1, you got one node. F3, you got two nodes. And now the next one is going to be three nodes, which would be F5. Now, for this one, we see a full wave plus a quarter. So 1 plus 1/4 gives you 5/4, which means that our wavelength is equal to 4L divided by 5. Or wavelength 5 equals wavelength 1 divided by 5. And finally, this was F3. Our F5 would be 3V over 5V over 4L. 5V over 4L. Finally, what this means is that our F5 is 5 times the original frequency, F1. Okay, take a deep breath. I know it's a lot, but let's go ahead and summarize everything that we've learned up to this point. Take away all this stuff. And let's look at what happens in our two scenarios. So when you have two open ends, the behavior is exactly like a standing wave on a string. So if you look at your formulas, you got your frequency 1 is equal to V divided by 2L. Your wavelength 1 is equal to 2 times L. Any number of frequencies after that, let's call those Fn, is going to be N times F1, and any subsequent wavelengths, let's call that wavelength N, is going to be 2L divided by N. Actually, no, let me not do that. Wavelength 1 divided by N. So to get your new frequencies, you just multiply by the number of harmonics, and for your wavelengths, you will divide by the number of harmonics that you have. So in this situation, N could be equal to 1, 2, 3, any whole number. Greater than 0, strictly greater than 0. Okay, but for your closed ends, your open ends, so I'm going to write this in a different color. Let's do blue. Your frequency 1 is not going to be V over 2L anymore. It's only going to be V over 4L. And your wavelength 1 is equal to 4 times L. Open end, we have strictly odd number harmonics that exist. Okay, so our Fn, not sure why this keeps happening to me. Our Fn is going to be N times F1. Our wavelength N is going to be wavelength 1 over N. And our N can only be equal to 1, 3, 5, etc., etc. Any odd whole number greater than 0. Okay. Open ends. F1 is equal to V over 2L. Wavelength 1 is equal to 2L. To get frequencies after that, you multiply by the number of harmonics. To get wavelengths after that, you divide by the number of harmonics. You can use any whole number greater than 0. When you have one open end and one closed end, you can only have odd harmonics. So your F1 is going to be V over 4L, and your wavelength 1 is going to be 4L. Same equation as last time, but now your n numbers, your harmonic numbers, can only be 1, 3, 5, 7, 9, 11, etc., etc., etc. Odd whole numbers greater than 0. All right. Let's look at a few examples and wrap this up. Okay, first example. An organ pipe is 1.12 meters long. What are the fundamental frequencies and next two harmonics and their associated wavelengths if A, the pipe is closed on one end, and B, the pipe is open on both ends? All right, let's look at A first. Okay, for A, first of all, I want you guys to notice that we're being asked to find the frequencies and wavelengths. However, we don't know what the speed is. But if you think about it for a second, an organ pipe, which is like the organ that you find in the church, is something that produces sound through the air. Therefore, it's going to be traveling at the speed of sound. So we're going to use that number for both parts A and B. Here's what we know. The speed of sound is 343 meters per second. And we know that the length of the pipe is 1.12 meters. All right, so for part A, we're looking at closed on one end. So remember, this is when we only see our odd number harmonics. Let's calculate our first wavelength first. That's going to be equal to 4L, or 4 times 1.12 meters. So wavelength 1 is going to be, doing some math here, 4.48 meters. That means that the next possible harmonic is going to be wavelength 3, 4.48 divided by 3. And then the next one after that would be wavelength 5, 4.48 divided by 5. So that one is going to be equal to 4.48 divided by 3, approximately 1.49 meters. And this one is going to be 4.48 divided by 5, approximately 0.896 meters. Take a look at these numbers. As our frequency gets bigger and bigger and bigger, we see that our wavelength is getting smaller and smaller and smaller. That makes total sense with what we know is the behavior of waves. Higher frequency, lower wavelength, and vice versa. Now let's look at the frequencies. So our fundamental frequency, F1, is V over 4L. So we're going to do 343 meters per second divided by 4L. Now we already calculated that. That was 4.48 meters. So our F1 is going to be, if you drop this into your calculator, it's going to be 229.8 or something like that. I know it's not three significant figures, but let's just leave this as 230 hertz. Okay? The next possible frequency is going to be F3, 3 times 230 hertz. Hold on. Made a mistake. I'm sorry, guys. I'm looking at notes that I wrote before I made the video. They're a little messy. 343 divided by 4.48. Okay, 76.6 meters, hertz. So my next possible frequency is going to be F3, 3 times 76.6 hertz. That's the one that's equal to about 230 hertz. And then finally, the next possible frequency will be F5, or 5 times 76.6 hertz. That one's equal to approximately 383 hertz. Okay, so the fundamental frequency is 76.6 hertz, and its wavelength is 4.48 meters. As we increase that frequency, you see that the wavelength gets smaller. And again, that makes sense with the answer. With the behavior of a wave. Now let's see how those answers differ if we have it open on both ends. Actually, let me do this. Let me delete this layer. Let me duplicate this one. Turn that one invisible, and let's erase all this stuff here. That erase it nice and big. All right. Make this one a little smaller. Okay. Okay. Now, part B of this problem. Again, we got the same length, same speed, but now it's open on both ends. Now, when it's open on both ends, the original wavelength is going to be twice the length. So 2 times L, or 2 times 1.12, which is equal to 2.24 meters. The fundamental frequency, F1, is going to be 340, well, no, let me not do that. V over 2L, 343 meters per second over 2.24 meters. All right, so for that one, 343 over 2.24 gives me about 153 hertz. Now, remember, when you have two open ends, the behavior is the same as a normal standing wave, so all of the harmonics are possible. So the next possible one would be F2, and the next one after that would be F3. Wavelengths are going to be wavelength 2 and wavelength 3. So this is going to be 2 times 153, and this one's going to be 3 times 153. This one is going to be 2.24 divided by 2, and this one's going to be 2.24 divided by 3. All right, so for F2, we will get 306 hertz. For F3, we're going to get 459 hertz. For wavelength 2, we will see 1.12, the original length of the pipe. And then for wavelength 3, will be approximately 0.747 meters. Again, just like before, as your frequency increases, your wavelength will also decrease. All right, let's look at some examples that are going to be similar to what you're going to see on Khan Academy. Okay, this guy says, the following standing wave vibrates at a frequency of 2,400 hertz. What is the next lowest possible frequency? Here is what you need to do to answer this question. First, you have to determine, do we have two open ends or only one open end? When you look at it, it's very clear that you only see one open end. So we're only going to see our odd number harmonics. The next thing you need to determine is how many nodes do you have? Here we see we have two nodes, one open end. Therefore, this corresponds to F3. Okay, our F3 is 2,400. The question is asking us to find what is the next lowest possible frequency. So since we have one open end, the next lowest possible frequency must be the fundamental frequency F1. If I was to ask you what's the next highest possible frequency, it would be F5. So we got to find the fundamental frequency. Remember, our F3 is equal to 3 times F1. So we got 2,400 hertz equals 3 times F1. So we divide both sides by 3. Cancel that out. F1 is equal to 2,400 hertz over 3, which is equal to 800 hertz. There's your answer. Next. What is the next possible wavelength for the following wave? Now, this is the type of problem that a lot of students have trouble with because there are no numbers. It's just all symbolic. But we're going to apply the same strategy as before and take a look at what is happening on the ends and then looking at the number of nodes we have. So here we see two open ends. So we know that all of the waves in this type of scenario behave the same as a regular standing wave on a string. We see hold on a second. We see two nodes and we see two open ends. Which corresponds to our second frequency. Now the second frequency has a wavelength 2 of just the L. The next possible one, this is just recalling our formula. Remember, wavelength N is equal to wavelength 1 over N, and we know that wavelength 1 is 2L, right? What we see here is N equals 2, but what we need to look for is N equals 3. So our wavelength here is going to be wavelength 3, wavelength 1 over 3, which is wavelength 1 equal to 2L, 2L over 3. L over 3. The next one will be 2L over 4, which would simplify to L over 2. Next one will be 2L over 5, and then you can kind of go on forever with that one. Okay, last one. What is the next lowest possible wavelength for the following wave? Now this one looks a little bit crazy, but it's still the same concept. Still the same concept. What do we have going on at the ends? And how many nodes do we have? Okay, we see we have 1, 2. Let's see, let me do it so you can see it. 1, 2, 3, 4, 5 nodes. 5 nodes. One open end. one open end. All right, let's do it this way. We know if you have one node, that's for F1. Two nodes gives you F3. 3, 4, 5 nodes. I'm just going to do this so you know that we're talking about the same thing here. So remember, you only have odd number harmonics for an open-ended column like this one. So the next one would be F5. This one would be F7. And the one that we have present here is F9. The next possible lowest wavelength for this one has to correspond to F7. Okay? So when you have wavelength 9, this is going to be 4L divided by 9. Wavelength 7 would be 4L divided by 7. And that is the next possible lowest wavelength. Okay? So if you were to follow the pattern, you would see 4L, 4L over 3, 4L over 5, 4L over 7, 4L over 9, etc., 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 etc. Okay, so those last 3 examples that we looked at are going to be the typical problems you'll see on the Khan Academy assignment. So I hope this helps. Just remember this page right here, the summary of what we just talked about. We're talking about standing waves in air columns. This could be either 2 open ends or only 1 open end. When you have 2 open ends, you have all the possible harmonics. The fundamental frequency is the speed over twice the length of the column. And the fundamental wavelength is twice the length of the column. When you want to find the next number of harmonics over, you multiply by the number of harmonics that you have. And the associated wavelengths are the fundamental wavelength divided by the number of harmonics. When you have 1 open end, your fundamental frequency is the speed over 4 times the length of the column, and the wavelength is 4 times the length of the column. Same equation, multiply by the number of harmonics to get your next frequencies, divide by the number of harmonics to get your next wavelengths, but only the odd number harmonics are possible here. That is harmonic 1, harmonic 3, harmonic 5, etc., etc. Okay, so that's it for this video. I will be posting this in a little bit, and have a great day.